Have you ever wondered that how we can find the roots of an equation without solving it algebraically? Imagine cutting an interval in half step by step until we pinpoint the exact solution. That's the power of the bisection method. In this video, we will break down the bisection method graphically step by step. We will see how it works, why it's so effective, and how it guarantees finding a root if one exists in the interval. By the end of this video, you will have a crystal clear understanding of how this method works and how to apply it. So let's start. Here we're drawing our axis. This is y-axis and this is x-axis. This is x-axis and this is y-axis. And this is some random graph of a function. The graph shows the function y is equals to f of x. So this is our function y is equals to f of x plotted on a Cartesian plane with clearly marked x-axis and y-axis. So the curve crosses the x-axis and we call that point P, indicating that there is a root in this region. Now our objective is to locate the precise x value where f of x is equals to 0 using the bisection method. So the method begins with the 2 points A1 and B1. So this is one point and this is another point. This is our point A and this is our point B. So this is our interval and we draw it from A1 to B1. Now the method begins with the 2 points A1 and B1 such that the functions have opposite signs at these points. So let's suppose if we put a point into our function, they gives us a value less than 0, which means that the value is negative and function is below the x-axis. So it is somewhere here. We call it f of a. And if we put b point into the function, so they give us a value greater than 0, which means that the function is positive and above the x-axis. So it is somewhere here. So we call it f of b. Since the function changes sign in this interval, so the intermediate value theorems guaranteed that there is at least one root between the point A1 and the point B1. So the initial interval is marked at the bottom of the graph, that is A1 to B1. To define the estimate of the root, we compute the midpoint of the interval by using a bisection method. And the bisection method formula is P1 is equals to A1 plus P1 divided by 2. And according to this formula, we will find the midpoint of the interval and it is somewhere here. We call it P1. And if we locate at x-axis, so this is here P1, that is almost near to P. That is our exact results. Okay, so again we put back this P1 into the function and we will locate that what is the sign of that P1. So if P1, f of P1 is exactly equals to 0, we have found that the exact root and the process stop. Otherwise, we will check the sign of f of P1. So let's suppose the sign of f of P1 is greater than 0. So which means that this function is positive. So the root must be between A1 and P1. It means that root from A1 to P1. So we call it A2 and we call it not P2, it is B2. So the function is positive. So it must be somewhere here. So we call it f of P1. Now we will go for the again same procedure. We apply the bisection method and that is P2 that is equals to A2 plus B2 divided by 2. And again we locate the midpoint. So this is the midpoint and we call it P2 and here it is P2. So again, we put back the value of P2 back into the function, and we will see the result of f of P2 is less than 0, which means that the function is negative. So the root must be between P2 to B2. From P2 to B2. So this is our next approximation, that is A2, and this is A3 and B3. So we call it A3 and B3. So again, we will apply the bisection method, that is B3 is equals to A3 plus B3 divided by 2. So this is the midpoint. And if we search here, so here is the midpoint. So this is P3. So this process repeats, and in the graph, we will see clearly progressively smaller intervals, representing how the interval shrinks around the root. With each iteration, the interval size decreases, and eventually the difference between B and A become very small, meaning that we have a highly accurate estimate of the roots. So the final approximation gives us the best estimate, and that is the result is f of x is approximately equals to 0. So if we see the P3 is very near to P point other than P1 and P2. So, the bisection method is a simple yet a very powerful approach to the root finding. Graphically, we can see that how interval is repeatedly halved, leading to a very precise approximation of the roots. So, if you found this video helpful, don't forget to like, subscribe, and hit the bell icon to stay updated on future tutorials. So, let me know in the comments if you have any questions. Thank you for watching and see you soon in the next video. Take care.